speaking from. Hi, today we have Mary Scott visiting via Zoom to give us a talk about her work at UC Berkeley. She's a professor in the Material Science and Engineering Department, and also is lucky to use the wonderful facilities up the hill in the Molecular Foundry at Lawrence Berkeley Laboratory. Mary got her PhD from UCLA in 2015, and then moved to Berkeley first as a postdoc and then as assistant professor. She's going to talk about using artificial intelligence to recognize objects inside electron microscope images. And it's a super hot field right now with neural nets and all that. Back in the age zero, I used to look at neural nets in the 1980s with op amps of all things. And at some point I said, oh my cell phone is racing ahead of the neural nets. And so then we didn't do it about 1990. But now I was visiting Berkeley to give a talk, and the hottest thing was the neural nets. And it turns out if you're Google and you have that kind of power, it's radically better. And it's just the really hottest thing right now. And so she'll be telling us about that. Thanks again for coming to visit.
Thank you so much for the very kind introduction. I'm very excited to present this work today. So I'll go ahead and share my screen and then hopefully confirm that everyone is seeing the appropriate presenter view. Great. Well, thank you so much for the very kind introduction. As was just mentioned, my name is Mary Scott, and I have an appointment both at the Material Science and Engineering Department in UC Berkeley, as well as the National Center for Electron Microscopy, which is part of the Molecular Foundry User Facility at Lawrence Berkeley National Lab, which is very close to UC Berkeley. And today I would like to talk about using some artificial intelligence strategies to extract information from electron microscopy data. So as an outline of my talk, I'd like to talk a little bit about why we want to do this, and in particular, how our approach might need to be customized or a little bit different than the approach that Google might take to build large libraries of imaging data for interpretation and training of neural nets, for example, for self-driving cars or other applications. And then I'd like to give really two examples of our approach in practice. I'll describe a multi-step pipeline that we built to identify defects in quantum dots. And then I would like to talk about overcoming problems of label noise, and in fact, treating label noise as a good thing, and using the convolutional neural net's inherent robustness to label noise to identify chirality or label chirality without pre-labeling a data set. And then I'd like to talk a little bit about upcoming technologies in electron microscopy and where there's a lot of work being done in very fast electron detectors that should be more and more standard technology that could be incorporated into these same pipelines in the future. And so with that, I'll dive right in. So I'm an electron microscopist by trade. And so if you ask me how to solve your research problem, I will tell you that electron microscopy can give you all the information that you need. And it's very true that advanced and modern electron microscopy these days can really give you incredibly detailed and rich information about materials, particularly nanomaterials, which is what we primarily study in my research group. And so critically, what we want to do is to use this electron microscopy information to understand and design a better nanomaterial functionality. And ultimately, what we would like to do is incorporate TEM robustly into high throughput analysis workflows. So as an example of the kind of information streams that we can get from electron microscopes, I'm showing some of my previous work from my PhD, where using electron tomography and studying tungsten, we were actually able to localize thousands of individual atomic coordinates in X, Y, and Z using electron tomography with precision on the order of tens of picometers. And this information and way of parameterizing our electron tomography data by simply being able to extract XYZ coordinates is then something that we can connect to first principles calculations, which is a wonderful and beautiful example of being able to connect our observation in the microscope to a metric for functionality. And similarly, a really popular newer analysis method, or I should say imaging modality in the electron microscope is scanning nanodiffraction. So if you're not familiar with this imaging mode, then what's happening here is we're converging our electron probe to a very small confined region, and we're rastering it over our sample. And at each raster point, we're actually collecting a full diffraction pattern. And so this data is called 4D STEM data. So the 4D stands for the four-dimensional nature of the 2x2 raster. And at each raster point, we collect a 2x2 full electron diffraction pattern. So this is a wonderful imaging modality that's very sensitive to microstructure on the nanoscale and can be very multimodal in how you actually interpret those diffraction patterns that come out. So what is the drawback of these what I'm calling amazing techniques, and why are you not able to walk into a microscopy facility and push a button and have this type of analysis happen automatically on your samples of interest? The answer is really time. In the case of electron tomography, it can take months to years to obtain the data set that you need and reconstruct and analyze it in a customized analysis workflow. And in the case of scanning nanodiffraction, because we're collecting a grid of two-dimensional diffraction patterns, our data sets can actually be gigabytes to terabytes in size. And so this just becomes intractably large. It cannot be analyzed by a human being manually. So we need to have another approach to extracting information from electron microscopy data streams if we ever want to robustly incorporate analysis methods like these into materials design and analysis workflows. And this is especially important right now because we're really entering an age of high throughput materials design. Automated synthesis and characterization capabilities are on the rise. This is inspired by many ongoing projects, but some that are local to Berkeley that are highlight would be, for example, the materials project, which has enabled high throughput materials screening for a variety of applications by collecting computational and experimental repositories. At the Foundry, one of the specialties of other facilities that I'm not part of is actually automated and combinatorial synthesis performed by robots. So this robot that is named Wanda, that is developed and run by Dr. Emery Chan in the Inorganic Nanomaterials facility, can actually make a library of nanomaterials or nanoparticles for you, vary composition, reaction time, or reaction temperature, whatever synthetic variable you want to control. And then you can look at the array of functionalities that you get from that library and decide which one is best. And similarly, this is some work from Jim Lebeau at MIT, where he's developing pipelines for automated CEM data acquisition. So increasingly, we can automate the data acquisition, the synthesis, and even have tools to guide in a very broad way what materials we should be studying. And TEM information extraction lags behind. But TEM is a really critical characterization tool for nanomaterials. When we're considering a synthetic optimization, population heterogeneity is an aspect of our measurement. In some ways, every nanoparticle is unique. So if we want to go from a conceptual idea of a synthesis to a very precise synthesis with shape or even a defect control, then we need to understand our population evolution during synthesis. And we also need to be able, or to be sure, that the structural variations or key structural features that we're observing in our data, we need to be sure that they are what is driving our bulk properties. And all of this really motivates a need to to understand not just distributions of size, shape, structural defects in our nanomaterial populations, but also correlations between the two. So how can we do this using electron microscopy? Well, we need to be able to rapidly extract information from TEM images. So here would be what I would say is a goal. We already have the ability in many ways through work pioneered, again, for example, by Dr. Emery Chan, to create synthetic populations over large parameter spaces, large synthetic variable parameter spaces. And then what we would like to do is design a data pipeline that can reduce or simplify our data into classified units and then analyze the statistics of those units. For example, units might be aspects of nanoparticles like size, shape, crystal structure, or defect content. And so with that, I'll go into the first example where we did this on a set of nanoparticles and built a two-step pipeline to identify a known class of defects using deep learning. So recent advances in machine learning, specifically convolutional neural nets, have really enabled a lot of application in computer vision in the past decade or decades, I would say. In general, this has been an extremely successful approach for image segmentation. So image segmentation here, I'm going to be talking about pixel-wise segmentation, which is creating a map of pixels that classify my image. So in this map, I am labeling the pixels that contain a nanoparticle as yellow and the pixels that contain the background substrate on which those nanoparticles are sitting in this bright field TEM image as purple. So what we would like to do is to develop an accurate generalizable pixel-wise segmentation approach for high resolution transmission electron microscopy images. And we're motivated to study bright field TEM, which if you're a TEM expert, you would know that this is kind of a vanilla or standard TEM imaging modality. It's not the complicated NanoDiffraction multimodal modality that I introduced first. And this is really because so far our experience has been that we're closer to being able to automate imaging modes like this than some of the more complex imaging modes. So this was the reason for our starting off point. It's also dose efficient and is commensurate with other experiments like cryogenic experiments where you might vary the temperature, or in situ experiments where you might care about time resolution of your real space images. Okay, so we decided to use for our first approach a UNet, convolutional neural net architecture. So in the typical convolutional neural net architecture, we're going to have an encoder and a decoder portion of our neural net. So the encoder portion will be performing, in addition to the filtering operations, a series of downsampling operations. So our data will get more and more abstracted as we move through the layers of the encoder. And what's different about a UNet than just a plain encoder-decoder convolutional neural net is that the UNet actually preserves some of the early layers of our of the encoder and concatenates them with later layers. And so this is a strategy that was intended to preserve smaller spatial frequencies, which we felt would be important for our atomic resolution electron microscopy data stream. So this was our design strategy, and we were also motivated by the fact that similar approaches, so this UNet is actually the original UNet that was published in Ronenberger's paper where they segmented HeLa cells from optical microscopy data. And similar approaches have been used to identify point defects in scanning transmission electron microscopy data. There's a lot of great work out of Oak Ridge showing this capability in two-dimensional materials. So this was our motivation for choosing this particular architecture. We did build our own UNet. Our architecture strategy was to start with something that really resembled the original UNet and prune layers and the depth of layers until we had sufficiently reduced our trainable parameters such that we weren't overtraining on our data set. Because our data set is not ImageNet. In electron microscopy, it is very time consuming to take even 1,000 images. So we are typically limited to hundreds of images when we are training our neural nets, and therefore we need to lighten up our neural net architecture to avoid overfitting or memorization in our neural net. We also found it really important to carefully define our classes. So our feature space in electron microscopy data, I'm just going to skip to the next slide so you can see what some representative images look like. Our feature set is much more limited than natural images that you might find in ImageNet. Here we really only have background and nanoparticle. The background is fairly uniform in the types of features it contains, and our nanoparticles have varying crystal and features and sizes, but other than that, there's not a lot of variation. So this is also something that we felt this made it valid to lighten up our neural net. And so we defined our two particle classes, our two classes, particle and background. And then our last step will be to define a threshold on the particle segmentation map that maximizes the pixel-wise accuracy on the test data. So we applied to two data sets, a very high Z, high atomic number nanoparticle, which is gold, and a low Z hard example case, which were cadmium selenide particles. And so these are the representative images of the two. If you're not a trained microscopist, you're probably finding it very difficult to see the CAD cell nanoparticles at all. So here's a contrast boosted image with some labeled for your, so you can see them by eye. And so these are our two cases that we wanted to test in our evaluation of this approach. So initially, we only trained on the gold data because we felt the labeling was much more accurate. And this worked well in terms of pixel-wise accuracy and segmentation for our gold data. But then when we tried to transfer, to generalize this neural net and apply it to our CAD cell data stream, it failed drastically. And so the results here are really captured both visually here and just the visual comparison between the human labeled and the predicted segmentation maps, where again, yellow is the particle class and blue or purple, depending on what you think that is the background class. And they're also, the pixel-wise accuracy is summarized in this confusion matrix here shown in C, where the numbers that we want to maximize are the numbers on the diagonal. So these are our true positive cases. So accurate background prediction pixels are in the upper left, and accurately predicted particle pixels are in the lower right. So we see reasonable accuracy in the gold case, but we see terrible accuracy in the CAD cell case. It's not well captured in the confusion matrix because it's just guessing that everywhere is a particle, and therefore guessing correctly that most of the particle pixels are particle. But this is obviously visually, and if you look at an intersection of union type error metric, this is going to be a failed case of application. And also, unfortunately, when we trained on specifically only the cadmium selenide, so only that hard example case, we also failed to accurately segment our CAD cell nanoparticles, even failing in the task of identifying the location of all of the particles, even if the neural net did not predict the boundaries very well. So this is unfortunate, but what we learned actually was inspired by some kind of common knowledge from the machine learning community that if you have more diversity in your data set, so you just have more examples of each type of data, then you tend to increase the accuracy of your trained neural net. And so we actually found that, interestingly, when we train on both gold and CAD cell, we improve the accuracy not only of the CAD cell, but also of the gold. So the true positives for the particle class pixels in both cases is greatly increased. And also by the dice coefficient, which is really an intersection of union type error metric that looks at the overlap between the predicted segmentation maps for the particle class. They're also greatly improved and reasonable values for this field. So we found that, similarly to the natural image community, training on a diverse data set actually gives increase across the board. We also, because we are microscopists and we already have a big toolbox of image interpretation techniques, we wanted to compare how our approach works to some more basic or classic non-AI ways of creating segmentation maps. So we could look at something like a threshold. So this is a threshold that's created automatically based on the histogram information from our images. And we see it doesn't operate so well. We can use some prior knowledge, actually, about the lattice spacings in our material and create a Fourier filter to try and create a segmentation map. This works okay for gold, but not well at all for the CAD cell, which has a lot more disorder in its atomic lattice. And so here again, we find that the UNet just visually is much closer to the ground truth. And so even from the perspective of creating something that is for a very specific application, we're still outperforming these traditional methods that we took and really tried to optimize for each individual data set. Okay, and then this is a little detailed, so I think I'm going to go through this quickly and not dwell too much on the specifics for this discussion. But we are also very curious about our network optimization. We had really done this in a way that was not terribly systematic, really just with this single goal of not overfitting. So we wanted to know, does our choice, if we keep the basic UNet architecture, does our choice of encoding architecture, so these operations that are occurring on the encoding side, actually affect our performance? And to do this, we actually explored several just widely available in the machine learning community encoder architectures. Without getting into the detail of the different choices that each of these make, these are all sort of designed with the idea of being lightweight and fast to train. Particularly MobileNet is optimized to try and run on cell phones. And although they have different choices in many of their architectures in terms of what is their stride, what is their downsampling strategy, one thing that we can kind of compare across the board is just the number of trainable parameters. And so this was something that we found to affect our accuracy previously in our custom UNet architecture, and we wanted to compare it on these that are out in the community for everyone to use. And we actually found that the architectures with the fewest parameters actually perform best. Whether or not you look at the intersection of union type error metrics or the just cross entropy loss. So this was kind of a nice result that we were happy to hear, because this has been the most commensurate with working with small numbers of images, which we anticipate really always having for the problems that we aim to solve in electron microscopy. And visually, we can also see that MobileNet, just in terms of capturing every nanoparticle in this hard case of CAD cell, does outperform the other two. So that's just a little bit of exploration of different encoding architectures. Although I will say that we didn't see a huge change in the accuracy from architecture to architecture. And there was a pretty big variation in the number of trainable parameters. So this led us to think that other aspects of training, such as label noise, which is when you have improper labeling in your data set, may also be limiting accuracy. And finally, just to round out this discussion of our two-step pipeline, I wanted to show results. So once we have segmented our nanoparticles, we are free to put those segmentation maps into existing tools that are part of scikit image, for example, the Python package, which can immediately tell us size, shape characteristics like aspect ratio, and can summarize those statistics for us on a particle by particle basis. And then we wanted to do one more thing, which was actually to look at our subset of the CAD cell data and train an artificial intelligence to actually tell us whether or not we could see a stacking fault in the CAD cell nanoparticles. So CAD cell has this very characteristic stacking fault defect that can occur, and it is under discussion in the literature as to whether or not this really affects the optical properties of these quantum dots. So we wanted to build a tool to detect these, and we wanted to be able to feed in the output of our convolutional neural net into that tool. So we decided to use a simpler classifier called a random forest classifier. So this is essentially an ensemble of decision trees, basically a flow chart style decisions. So is going to be a featurization of our data. This means that we take our images and turn them into feature vectors, where the items in the feature vector come from image filtering operations like rotational averaging on the real space or Fourier space image. And then we actually create an ensemble of these decision trees, each of which will make a class prediction based on those feature vectors. And then based on this ensemble decision, we determine the final class. So we're inputting directly we're inputting the segmented regions directly out from our neural net. And then, for example, the classes could be, yes, it has a stacking fault. No, I can't see a stacking fault. No particle. And I can't tell if this should be a stacking fault, which actually turns into two classes. And so our final classification results are shown in this confusion matrix. So our categories are agglomeration, which means the particles are overlapping and the neural net or the classifier can't tell whether there's a stacking fault. There's no particle present, which we did include as a test case because this is a possibility for a real pipeline that would mistakenly be included. There's no stacking fault. It's misoriented, and I can't tell because of I don't have atomic resolution in the image, or it's properly oriented and I can indeed see a stacking fault. So the yes stacking fault prediction is correct 80% of the time, and the no stacking fault prediction is correct 92% of the time. So these are very good results, and when coupled with our convolutional neural net, provide a workable modular pipeline that can actually classify our resultant images according to whether or not they contain a known feature. And another reason to use the random forest classifier is because it's very fast to train. So you could easily envision applying this approach to a different data set with a different known defect and quickly getting the results that you need. All right. So next, I want to talk a little bit about one of the things that I mentioned as being a problem and really an unknown in our first pipeline, which is that we don't always know that our labels are perfect in our training data for our neural nets. And the system of study here is actually going to be chiral nanomaterials. Chirality, of course, is this as a property of an object where it cannot be overlaid onto its mirror image. And this property exists in nature on many length scales, such as molecularly, on the nanoscale and chiral inorganic nanomaterials. which are what I'm interested in this study, and then of course larger length scales in our natural world and universe. So the materials that we actually are studying here are tellurium nanoparticles. So this is a collaboration with Asaf Ben Moshe, who is until very recently a postdoc with Paul Alivisatos at UC Berkeley, as well as Wolfgang Theiss at University of Birmingham on the automated imaging side. So our goal is to determine population statistics for left versus right-handed chiral nanostructures, and our test case are these tellurium nanoparticles. And we need to use scanning electron microscopy in this case because transmission electron microscopy would be ambiguous. We would not be able to tell the chirality in that imaging mode. And the reason that we want statistics on the occurrence of handedness here is because the synthesis of these materials is not perfect. If we want to obtain size and shape control alongside perfect control of chiral population, then this has not yet been achieved. And so what particularly Dr. Ben Moshe is working on is understanding the synthesis science behind the production and later the optimization of these chiral nanomaterials, which could potentially have many applications in optoelectronics, biomimetics, and et cetera. So we want to ultimately turn this pipeline into a synthetic study of the growth of these nanomaterials. And so the approach would look something like this. We segment out our particles from our SEM data stream, which actually is able to be automated on our SEM at Ensemble. We take many images and segment out many particles. We classify them according to orientation, and then we classify them according to their handedness. And example right-handed and left-handed nanoparticles are shown here. And so one idea that we had in analyzing this data, because we were in the situation where we had much more data than we can label by hand actually, was what if we could generate a data set without actually labeling and take advantage of the special property of chirality that these nanoparticles have. So if we have raw data that we know is mostly right-handed just from initial inspection during the experiment, and we mirror it, then we've automatically created two populations, one that is right-handed dominant and one that is left-handed dominant. And so if we could combine these into a unified data set by labeling the right-handed dominant data set as all right-handed and labeling the left-handed dominant data set as all left-handed, then actually what we have done is turn our classification problem into a label noise problem, because now those outlier nanoparticles that are labeled right-handed but are truly left-handed, we still want to detect those, and we've mislabeled them, but we're going to use the convolutional neural net approach, which in the literature has been shown to be robust to label noise. So that means that the convolutional neural net can learn the features of objects and correctly classify mislabeled objects that might occur in the training data. So to actually do this, we first needed to understand how well the convolutional neural net could overcome the varying levels of label noise, because in practice, our label noise would be unknown. So we decided to test our approach, not just using the SEM data, but also using some MNIST data. We chose the number 7, which is chiral, and artificially generated varying levels of noise from an initially 100% right-handed data set. So here's actually how this works. So we start with all right-handed 7s, and then we mirror a known subset of those. And then we call that our right-handed training data set. Then we mirror all of them, and this flips all of the labels and keeps the same amount of label noise, and we label those as our left-handed. And then we create a unified data set that has equal representation of left and right with a known label error. And we're going to adopt this strategy first for the MNIST 7s, but also for our chiral nanoparticles that are right-handed and left-handed. And we have approximately 2,000 right-handed images for each data set in this application. So initial testing of training a convolutional neural net to predict the right or left-handed label for the 7s from the MNIST data performed extremely well. It was able to learn the representation nearly perfectly for most error values. So percent error in the training set, so this is the error that we gave it, and the training set is on the x-axis, and the average accuracy according to the ground truth clean validation set is here on the y-axis. However, it does begin randomly guessing after 40% label noise, which is to be expected. It just can't learn the representation. Applying this to the chiral nanoparticles shows slightly less high accuracy, but still very good success, and demonstrated an ability to be robust to noise. So the trend line plotted here is the label accuracy that we gave it in the training data. And you can see that up until about 45% error, it stays above this, accuracy that we told it. So, however, it does revert to random guessing again. And to attempts to overcome this tendency to not be able to learn the important features to predict left versus right-handedness, we kind of took a practical approach, which is that, you know, any real researcher would be absolutely willing to label perhaps not 2,000, but definitely a smaller number of images from their data. So what if we actually did a two-step training process where we trained the first epoch of our neural net only on a very, very, very small data set? This will be problematic if we continue to train on a very small data set, because our neural net would almost certainly overfit. But for the very first epoch, giving it a small data set and then allowing the subsequent training steps to occur on the large full data set actually pushed our ability to overcome and learn the important features of the chiral nanoparticles closer to that 50% error in the training set. So this is really relying on that memorization effect and overfitting effect for the small data set for early feature learning. And so ultimately, we hope to incorporate this into a larger scale study of synthesis science. But what we've done here is take advantage of the geometric relationship of the right-handed and left-handed particles to do a case study of two different neural net approaches to in terms of overcoming label noise. And we find good results and good accuracy for this approach that mean that this could realistically be used to classify chiral nanomaterials without creating a large label data set. All right, and so in the last, I would say 5 to 10 minutes of my talk, aiming to leave time for questions, I want to give kind of an update of some progress that's been happening at Lawrence Berkeley National Lab, and some work in my group to deploy and use a very fast electron detectors that are currently under development. And so here I want to revisit this image. So I motivated this talk by showing some very modern and useful electron microscopy imaging modalities. But so far, we've only talked about HRTM and SEM data channels. So I want to talk a little bit about NanoDiffraction and some of the limitations for incorporating it into high throughput workflows, which actually aren't only data interpretation, it's really data handling as well. Because as I mentioned earlier in the talk, these data sets can be extremely large. So to refresh, a NanoDiffraction experiment rasters the electron beam over the sample and collects a full pixelated image of the diffraction pattern. Fast frame rate detectors are enabling this experiment to be performed routinely, but analyzing these data sets or even moving these data sets around from computer to computer is extremely time challenging. This is the reason that we're drowning in data. The so-called 4D camera is a project that's developed through some other folks at Ensemble collaborating with various facilities at LBL. So this detector operates at 87 kilohertz frame rate. And so that's the speed that it's reading out pixelated diffraction pattern images. This amounts to about 3.4, so about pi terabytes of data per minute. So not only do we have the issue of handling the analysis of this data, it's actually a computer engineering problem to even have this data land somewhere such that we can save it properly and use it. So this was something that we had to overcome at Ensemble. Of course, the reason that we want to perform this type of scanning nanodiffraction experiment is because there are a variety of information channels that we can extract from different nanodiffraction experiments. So for example, composition or strain mapping, just by analyzing the peak locations and diffraction patterns, typography, which is a phase retrieval method that uses interference between the probes and the diffracted beams, and the nanodiffraction experiments, or doing something like tracking the probe position to understand things like magnetic fields in our sample. So in many ways, the nanodiffraction experiments can be very multimodal. We can pull out more than one information channel from a single experiment. If, for example, in the case of composition or strain mapping, you could imagine classifying according to composition or crystal type or crystal orientation, and then further measuring strain. So these data channels individually can each be multimodal, but again, we need to handle this fire hose of data. So I'm going to give an example of typography and our kind of ability to perform very fast typographic reconstructions. So here's the actual architecture of our camera's data transfer. So here's a picture of the 40 camera installed on our TMO5 microscope at Ensemble. Here is kind of the layout of our data transfer, where we pipe it through FPGAs, it lands on some receiver PCs and is threaded back together. Then we undergo a process called electron counting, which actually takes the data from being a full frame image to an XY coordinate list of electron strikes, because this camera actually operates so fast that we can safely assume that any pixel that has intensity in it only corresponds to one electron hit. So after counting, we've greatly reduced our data size, so we can go from 150 gigabytes for a typical 512 by 512 scan taken in 3 seconds, down to, depending on the number of hits, anywhere from 2 to 10-ish gigabytes. And we basically go from FPGA to RAM to flash storage to sparsifying this data. So this counting process can take minutes. Here's our current timing and timing limitation. So it takes about 220 seconds to go from this data cube that's 150 gigabytes to an image that you can assess and then determine if you want to save for further manipulation or to delete because your experimental parameters are not what you want. Again, so that counting, the transfer to the counting PC and the counting operation itself takes about 2 minutes. And then we then additionally have to do some more transfer operations that we're trying to remove to get it onto the GPU to do our single sidebands. This is a non-iterative typographic reconstruction. That's sort of the most basic flavor of typographic reconstruction, and that takes about 17 milliseconds. So most of what we're doing here is copying data around in that counting operation. So this is 99% of our time. And really the processing actually only takes about 34 milliseconds. So if we didn't need to count separately, if we could just do this on our FPGA modules, we would save a lot of time. And if we could actually put the GPU on the data receiver PC after that, then we could get down to about 5 seconds from 150 gigabyte scan to beautiful images that look like this. So these are actually typographic reconstructions. These are on the left, a tantalum ditelluride nano ribbon that's stuffed into a multi-wall carbon nanotube. Then we have some amorphous carbon supporting gold nanoparticles. And so what's beautiful about typography is that it's really the best imaging modality to be sensitive to heavy and light elements. And it can be quite high resolution. And although this is not an iterative typographic reconstruction, there are more advanced iterative reconstruction approaches that we can take to post correct for things like improper defocus or microscope imaging imperfections. So having this fast typographic pipeline, which my postdoc, Philip Pels, is currently actually turning into a live interactive GUI from this incredibly fast data stream, represents a significant advancement just in the practical use of very fast electron detectors. All right, so that's it for my talk, and I think I've left plenty of time for questions, so I'm looking forward to that. Just to summarize quickly, a major goal for this branch of the research in my group is to incorporate advanced measurements in the electron microscope. Be those measurements made from automated imaging protocols that can create large libraries of nanoparticle imaging data that correspond to combinatorial synthesis efforts, or to utilize next generation electron detectors and to really have complex electron microscopy data streams like typographic reconstruction become almost instantaneous, and also to immediately reduce for experimental assessment data sets that are initially enormous. Both of these efforts really go towards trying to incorporate electron in a realistic way to high throughput materials design. And so I think with that, I will thank, of course, my group, not just for all the wonderful research that they've done, but for their incredible patience during this very strange remote time. I'm happy to report that actually my postdoc is taking data on the 40 camera right now. So after this talk, I can remote in and see how it's going. So another silver lining of the kind of remote and socially distant environment that we've had is, this enhanced capability to check in remotely quickly and log in to support PCs and diagnose problems for postdocs, even though I'm sitting at home right now. So of course, I'd like to thank my collaborators and my funders, and also everyone here for your attention, and also for inviting me to this seminar series. So with that, I'll have 10 minutes left for questions, and I think I could perhaps stop screen sharing, or maybe I'll need my slides.
Okay, well, thank you very much. Though we have one question already, but for those of you who would like to ask a question, please use the Q&A on Zoom or the chat, and then I can pick them up, and then she can answer it. So here's the question we have so far. It's how flexible can the neural nets be? ? Do you envision researchers sharing neural nets they have developed to help others with similar classification data extraction processes, or are they so specialized that researchers need to understand neural nets well and build their own to utilize this type of analysis?
Yeah, it's a very good question. So we find that for similar tasks applied to different types of materials, especially in HRTEM, the network generalizes well. We've applied it to data of different nanomaterials from different microscopes at a narrow but still close to atomic resolution magnification range, and we see acceptable segmentation. One thing that I'll mention, so I think that it's very generalizable if you have similar goals. If you have different goals, though, if you wanted to classify according to something that's a drastically different type of feature or information channel in your data set, it would be less generalizable. And to that end, one thing that I didn't get to talk about today is a collaborative effort to build a fast image generation pipeline, where we hope that we can build tools for researchers to generate reasonable physics-based TEM simulated images on timescales that are not too bad, that can then be used for training data. Because this is a way of generating training data for your problem, again, without having to label. And absolutely, we share our materials. I should have put maybe I can put it in the chat.
Yeah.
I don't know how to do that without sharing.
Oh, you can just type it in chat. It's good.
Let's see. I think I have to stop screen sharing to do that. Sorry. I'm just going to throw our, maybe while we go to the next question, I'll be pulling up our GitHub repo for the nanoparticle finding and classification tools.
Okay, great.
Um,
Well, let me do that so you can.
okay. I think that should go to panelists and attendees. So please,
okay, there it is.
Please take a look. And I know there are several efforts in the EM community to save both data repositories, or simulated and real, for folks to use to train. So Maria Chan's Atomize at Argonne National Lab, and Ho-Lin at University of California, Irvine also just published a paper that's TEM ImageNet for folks to train. So those are also some resources that you can check out if you have a specific task and you feel like our tools or the other tools you're finding won't generalize well to that task, and you need more training data.
Okay, thank you. There's a couple more questions. The next one is the labeling done using ground truth images, question mark.
Right, so the labeling is done using expert labels. So we use a Labeler app and apply that to the data taken by my grad students. So it's a good question. Is this the ground truth or not? Because definitely we can have label noise in those images. For example, the CAD cell data stream, even by eye, it's hard to see some of the nanoparticles. So the experts can fail at that task. And that's why I think it's really important that that our group and others are working on ways of generating perfect ground truth images that come from simulation. The key is that the simulation needs to be accurate enough that the neural net, what the neural net learns from it, is then applicable to real images.
Okay, thanks. The next question is, in the first case, i.e. segmentation using CNN, is it background and foreground separation, or is the network capable of detecting multiple features?
Right now, we just set it up as a 2-class problem. So we say that the nanoparticle case is class 1 and everything else is class 2. So it's not just background, it's if there's any schmutz or a hole in the film that then shows us some vacuum, that we also put as class 2. We found that to be the most accurate way of teaching the neural net to recognize the nanoparticle features.
All right, thanks. Another question. What do you see as the main bottleneck to adoption of these analysis techniques, question mark? Is it lack of training data, computer infrastructure, demonstrated success, or something else?
Oh man, I think there's a couple things. Like for me personally, not being someone who has a degree in applied math and is, I wouldn't call myself I don't develop machine learning approaches. I use them. So I think for me, one hurdle is really diagnostics, understanding where our predictive power is failing. Yeah, I think there's kind of an anecdotal saying about neural nets that they always work, and that's bad because sometimes it's not working, it's not recognizing the features that you would like it to, and can be that can limit the applicability. So I think just being able to broadly compare easily from architecture to architecture is something that will help that problem. Training data is a problem. It's very time consuming, even manually or automatically, to take 10,000 images of nanoparticles. It would take weeks. So we're building larger and larger training data sets. And again, we hope to to simulate to do this as well. And I think this is related to the question of computer infrastructure, because I think that what we really lack at LBL, and that I know that a lot of other research facilities like LBL are coming to realize, is that we lack a centralized data repository. It would be wonderful if these trained models that we're developing lived all in the same place for everyone who's developing models at LBL or even at other DOE scientific user facilities like Ensemble all together. And it would also be wonderful if our data repositories were co-located with those models all together. So I think who's going to make that infrastructure is still an open question, but I think the realization that we need it is happening very quickly at least at LBL for sure.
Okay. Another question, were the training data set acquired specifically for the work or any open access databases I'm trying to turn this into a question, were made use of these works? Were the training data set acquired specifically for the work or any open access databases were made use of in these works?
We acquired the data specifically for these tasks. For the segmentation approaches, we also tried using some pre-trained flavors of the BGG16 and ResNet that were pre-trained on ImageNet, because our thinking was often in early stages of training, you are learning to recognize very similar features like edges and corners and things like that, even in the real natural data versus our electron microscopy data. We didn't find a huge advantage to using the pre-trained neural nets though. And the reason for that, we think, is that actually our early stages of training on our data set looks different than early training on ImageNet. And I think it all comes back to feature diversity and the fact that the signal to noise in our data sets is actually quite high compared to natural images.
Okay, well, this is really exciting stuff. A lot of interest from the audience, and thank you again so much for giving the talk.
Well, thank you so much for having me, and thanks for the excellent questions. Like I said, this is a community, especially in electron microscopy, that is growing. So if anyone in the audience has interest in this topic and would like to follow up, please don't hesitate to email me or to check out our website or the GitHub.
Great. Thanks so much.
Hi, thank you.
Thank you so much. Bye-bye.